I'm gonna deviate a bit from wireless communication towards RF sensing. So this is my PhD title, like PhD thesis title, spectrum efficient HCS or human-centric sensing using millimeter wave FMCW radars. So first, I will talk about the structure of my thesis and the papers that I will include. And then I will briefly introduce the two works that I did on gesture recognition, which is like mid-field sensing. And the main part of the talk is about a paper that is recently submitted to IEEE letters, sensitive letters. But talking about my thesis, it has two, let's say, aspects. The first one is human-centric sensing, which means that we are trying to sense like most of the aspects that are related to like human, obviously. So in this field, we have like three different granularities, let's say, near field, mid field, and far field. In far field, we did localization with Christian, which was presented like last week in UCITCO. In mid field sensing, which is, let's say, the main part of my thesis, I have 4 papers. PointGest, which is published in MLSP, then Pantomime Inputs, then another MLSP, and the Tesla Rapture, which is published in TMC, or Transactions on Mobile Computing. And then in near field, I have 2 papers. The first one, body composition analysis inputs, and then the water quality assessment, which will be presented today. And I told you it's submitted to IEEE sensors. And then the other aspect is like JRC, or joint radar communication, and the motivation there is that obviously we have a limited spectrum for RF, so we're not gonna like make it more congested. Obviously, it's gonna be congested anyways, but we're trying to reuse the same frequency for communication and sensing. And in this, I have again 2 papers, sidelink channel, which I will briefly touch, published in TMC 2022. And then JRC using reinforcement learning, which is submitted to a communication magazine. So in Pantomime, the paper, which we published in 2021, we focused on gesture recognition. We proposed a system based on the radar, which is to recognize gestures, human gestures. And we collected the data set from more than 50 people with 21 classes of gestures. And we proposed a neural network and also a pre-processing pipeline to like, first of all, we go from ABC data to point cloud, which is like this. And then in the second step, the second, let's say, group of pre-processing, we go from point cloud, like super sparse point cloud, to, let's say, we sampled and like, you know, a bit more fine-grained point cloud. And finally, we process the point cloud using the neural network, which is proposed here. So basically, the structure of the network is super simple. We have like different frames, and in each frame, we have a different number of points. So we basically use the point net plus block for each frame. And then afterward, we have a few layers of LSTM to capture the temporal dependency. And at the end, we will have like a few fully connected layers. And then to better capture the spatial dependency, we have an aggregated block for the point net, which means that we simply aggregate the whole frames through time, and then we feed it to a point net plus block, and finally we have the class score. So we achieved an accuracy of 95, 94 in this work. Everything was good. But the problem was that, wait, what was the problem? I don't know yet. But the problem was this, actually. So the model obviously was super heavy because we had to process every single frame like separately. We needed a Tesla V100 GPU to feed the model in. So it was like 20 gigabytes of RAM and like 10,000 euros or something. So obviously it wasn't like good for embedded devices. And so it was like pointed out by the reviewers, and we were like, okay, in the next work, we can maybe address it. So in the next work, or Tesla Rapture, we went from like traditional processing of like temporal data to like graph-based. What does it mean? It means that, again, we have the same like pre-processing, which means we go from ADC data to point cloud. But in the second phase, like in the third phase, actually, because this was there in the Panther one as well. But in the Tesla, in the first actually step, we simply create a temporal graph from the point cloud. What does it mean? It means that we find the nearest neighbor for each point from the next frame, not from the whole point cloud. So what is the effect of this? Actually, this way we simply kind of reflect the temporal dependency of the gesture in the graph structure. And after that, having the graph structure, we don't have to go over and over on the data to capture the temporal dependency. So we simply use a GNN, graph-based neural network, to process the graph and to kind of classify the gesture. With this one, we achieved an accuracy of 99, 98, and then like in extreme cases like through wall sensing and stuff, we had super good accuracy, like almost 20% improvement, like compared to the state of the art. But again, we had another problem. And what was that? The problem was that, as I mentioned before, we were using the RF spectrum. So obviously, it was not really good from the standard, like from standardization perspective. Why? Because we were kind of interfering with the like licensed and unlicensed band for 5G. So we were like, how we can address this one? So we came up with another idea, which was about like implementing and integrating the proposed approach into 5G standard using sidelink channel. What is sidelink channel? Actually, it's released in I guess it's published in release 13 of 3GPP for 5G. And basically, it's dedicated for D2D communication. But we decided to use it for sensing. And what does it mean? It means that we have like multiple radars that are UEs. Let's say they are connected to the base station. So in this scheme, one of the radars communicate with the base station and acquire a channel. And then in the acquired channel, we simply do the sensing. So instead of communication, we perform sensing in that channel. And so each of the radars, they capture the data from their own perspective. And then they process the data, segment the data, and do a feature extraction, like the first few layers of the neural networks, the neural network. And then they share the features through the sidelink channel. And finally, after aggregating the features, we classify the gesture. So it was a kind of, let's say, the schematic view of the method that we proposed. So, but as you notice in all these works that I presented, we were actually in the midfield sensing. Why? Because the distance from the radar to the target was around 1.5 meters up to 5 meters. And we were using like point clouds for the data. So we were just trying to push the boundaries. And I was thinking, how can we use it for like, you know, like, let's say like near field sensing. So we came with this idea that maybe we can use it for water quality assessment. So we had this use cases before, like vehicular scenarios, like industrial scenarios and stuff. So we were like, since the radar is super small, so the radar is this one. And as you can see, compared to a watch, it's like super small and can be easily integrated into watch. So I was like, maybe we can go for a wearable smartwatch that is equipped with the radar, so that, like, for example, imagine you're hiking somewhere and you don't have access to, like, you know, like water bottle and stuff. So you just want to drink from the stream. So basically, you can just put your watch on top of the stream, like in a distance of like 5 centimeters or something, and it will tell you if you can drink it or not. Basically, it was the motivation of the work somehow. And some funny fact, actually, I created this picture using Dolly, so that's why we have like some artifacts there, but it worked perfectly, I guess. So, yeah. But anyways, let's. That's true. That's true. So it doesn't work like, you know, like a designer, but at least it saved my life in the sense that I don't have to design it myself. So, yeah. So, but let's talk about the radar, the principle of the radar. As I told you, it's an FMCW radar, namely IWR 1443. It works in 76 gigahertz frequency. and this is the signal that it transmits. Basically, it's a chirp. Yeah, what does it mean? It means like the sinusoid with increasing frequency through time. So this is the AC domain, and this was the frequency domain. The red one is a reflected one, and this one is a transmitted one. So it transmits the chirp, and then based on the reflection, we can get some insight about the target. So this is the radar which is installed on the watch. So you can see it's like super small. We have 3 transmitted antennas and 4 received antennas. Obviously, like 12 virtual antennas are there. So it means that we can get like 3D information like range, Doppler, and also angle. And this is the data structure I get out of each of these received antennas. So as you can see, it's like a complex signal. And we have the ADC samples there, so which means that we simply use an ADC converter to convert the signal to digital, because obviously it's analog. So we have the samples there in the first dimension. And then in the second dimension, we have chirps. So basically these are the chirps. And finally, we have the frames, which means that like the window that you have. So basically in each window, we transmit like different number of chirps. But in our application, since we are not interested into like the velocity, because we are just interested in the, let's say the how somehow the material itself. So we reduce the number of chirps, because if you want to estimate the velocity, you need to transmit like many chirps. But in this one, we increase the frame length and decrease the number of chirps. So yeah, and as I told you, we have like 4 of these cubes, each for each of those, let's say, radars. So 1 for each received antenna. So, and this is the, let's say, the schematic view of the radar. So basically, we have the synthesizer, which generates the chirp, and it transmits through transmit antenna. And then we receive the reflected chirp off the target in the receiver antenna, and we have a mixer, which mixes the transmitted and the received chirp, and we have the IF signal or intermediate frequency signal. And here you can see that like, well, the transmitted and the received chirps, obviously they are not, they don't have like fixed frequency through time, but when you subtract them, you will have a normal sinusoid, not a chirp anymore. So basically we will work on this signal to extract the information of the target. The thing is, I mean, I briefly mentioned the performance of the. Oh, sorry.
The small one.
Oh, okay. Okay. Wait, I covered the logo. Okay, so yeah, the performance depends on the configuration of the chirp. Here we have like a few, let's say, equations for the radar. As you can see, the maximum range depends on the bandwidth of the IF signal, which is fixed for the radar, and then the speed of light and the slope of the chirp. And also the range resolution. Actually, the range resolution means that the minimum distance that the radar needs to identify 2 targets as independent targets. Otherwise, if they get closer than this distance, they will be identified as a single target. And the range resolution depends on, again, the bandwidth and the speed of light. So these are, well, for our application, again, since we were just interested in the material of the target, we use the maximum bandwidth and the minimum number of chirps to kind of focus on the material itself. And but why do we think the radar can actually assess the quality of water? Based on the radar equation, well, we are just interested into this radar cross-section because the rest are like related to the radar itself, like the antenna gain, the transmit and the receive antenna gain, the transmitted power, the distance, and also the wavelength. But the thing is, we fix them all except for radar cross-section. So it means that in the experiment setup, we had the same distance for all the samples. Obviously, we use the same wavelength, but the radar cross-section was different. And what is the radar cross-section? Radar cross-sections depends on the target, like on the, let's say, the geometric features of the target, the size, I don't know, the texture and stuff. So basically, based on this equation, we believe that if you change the material of the target or the texture of the target, it's going to be reflected in the received power. So by analyzing the received power, we can theoretically we can identify like the material of the target. So this was the kind of, let's say, theory behind the work. And to show it like in a more practical way, we decided to conduct a very simple experiment. So basically, we have we put the radar in a 7 centimeter distance from the surface of the different types of waters. So in this one, we added like 0 gram salt. In this one, 30 gram per liter, and in this one, 60 gram per liter in the container. And so basically, we applied FFT for the ADC signal. So we have like, and then afterward we applied CPAR to identify the peaks. So for example, for this one, we have like 5 different samples. As you can see in this dimension, we have 5 different samples that we got from this water, and the FFT magnitude here and the frequency. So as you can see, we observe some similar patterns for this level of salt. And if you see this one, it's the same. So we have some similar pattern between the samples, and the same goes here. But the thing is, like, they are different from each other. So if you compare this to this one, obviously, I mean, there are still some similarities, but the thing is, they are different between different types of waters. So based on this, we think that the radar is able to identify different types of water, or let's say different types of contamination in the water. So here we have the experimental setup. As I mentioned, we have like the container, and then the distance from the surface of the water to the radar is like 7 centimeter. We use 2 different types of boards. The main one is like IWR 1443, but that one creates point clouds. So we needed to get ADC data out of the point cloud. So to bypass this first pre-processing pipeline, we use the DCA 1000 board connected to the radar. And for the water itself, we use 4 different types of water: RO, tap, river, and well. And as you can see, they have different characteristics, like physical characteristics, like turbidity, pH, or electrical conductivity. So basically, they are like per se, they are different. So, but how did we process the data? So we proposed a super simple, let's say, architecture. It's basically just a fully connected neural network. The only difference is that we needed to work with actually complex signal. So the input is a complex signal, not just a float number. And also the activation functions and all the differentiable parts of the network should be actually complex. So here is the input. So we have input H, which is complex, and then W, which is the weight, and that is also complex. So we have simple convolution there. And for the activation function, for the ReLU part, we apply ReLU on the imaginary part, and then in the let's say real part. And at the end, we have like simply absolute value for the output vector. So we apply abs on the output, and then we have like the class probability. So, but what about the results? For the results part, we actually we had 2 different ideas in mind. The first one was that we wanted to classify the source of the water. So in a sense that if it's a well water, if it's a RO water, like tap water or river water. So for the classification here, as you can see, like, okay, I forgot something here. We propose actually 2 different models. One is like 2D and the other one is like 3D, but what is the difference? If you remember, I said that we had 4 different received antennas. So in the 2D model, we assume that the antennas are completely independent. So we assume that the data from each antenna is a new sample in the 2D one. And in the 3D one, we kind of appended the data from different antennas to create a 4D cube, and then we fed it into the network. So in the results part, as you can see, well, the thing is, like, the innovation is in the application. So we didn't really have a competitor in a sense that we can compare to, like, I don't know, already existing models or something. But we still came up with some ideas to compare to, like the very basic one, SVM and PCA plus SVM. And then the neural network based like FFT MLP, which means that we performed FFT and then CFAR to extract the peaks, and then we compared, and then we use MLP to classify. So obviously, like the one that we proposed was better in terms of water type. And also we performed salinity level, let's say classification. We had like water with different levels of salinity. It's not a regression problem. Obviously, it should be a regression problem. But the thing is, since we didn't have enough samples, and it was like really time consuming, so we didn't go for regression. But in the future work, we were planning to go for regression to identify the exact level of salinity. And again, we achieved like 100% accuracy there. But what about the actually real contaminations like arsenate, fluoride, nitrate? With the radar, we showed in the paper that we can achieve an accuracy of like 0.5 gram per liter. So if there is like 0.5 gram contamination or above this value in the water, we can identify it using the radar. Obviously, in a controlled environment, like with this fixed distance and stuff. But I feel, I mean, well, for some of the contaminators like fluoride, it's like quite higher than the standard. So it might not be that useful for those contamination, but still for some other ones, it might be useful to use the radar. So basically, yeah, that was the presentation. So in the beginning, I mean, in the first part of my work, as I mentioned, that we went for mid-range, mid-field applications in HCS, like gesture recognition, and we proposed the first generation of our model or pantomime, and then we went for like, let's say the integration into 5G, and finally, we kind of pushed the boundaries to estimate like water quality. And in another work we did it like for body composition analysis and stuff, which is not presented in this one. But yeah, that's also considered as let's say near field sensing. So yeah, thank you so much. If you have questions.
No, you could answer the innovation we are waiting for. I have a question like, I mean, for the, you use this approach that you can basically take connectivity and access for the data to be more, to detect this type of water. You have a for the other ones that you have. Can you actually take this on molecular level? That's on the radar section?
What do you mean? You mean the like the contaminations like?
Yeah, I mean, the replication basically for bacteria.
Yeah. Well, yeah, as I told you, like the radar cross section depends on the material or material of the target as well. So when you add some contamination to the water, it changes the reflected power, and based on that, we can identify the let's say the contamination. But the thing is, like, it depends on not only the radar but also the processing pipeline. So I mean, I wouldn't say that the like 0.5 gram contamination per liter is the accuracy of the radar, because obviously I'm using my model to extract this, so it might be even better. You might be able to come up with a better model that is able to push the boundaries of the accuracy of detecting contamination. But yeah, based on the let's say the radar equation, it can affect the radar section. Well, that I can't answer because I mean, I don't know, but this limit is for the radar plus the model, but I'm not sure about the limit of the radar itself, actually. Yeah, sure.
I think it's more related to what Monica was saying. So at least in Brazil, like in my region also, was quite scarce, and whatever water people have, they take and they boil. So try to see whatever the other side. I was wondering if the temperature of the water at its boils of something?
Yeah, obviously the temperature affects the reflection pattern. But we've not studied the effect of temperature, indeed. But yeah, it's obvious, and that's why I said like it's super controlled, because the distance is controlled, the temperature is controlled, everything is controlled. So basically, it was a proof of concept work. So we have a lot to do actually in the future.
That's what I'm saying. I think that there would be a potential for actual marketing.
Yeah.
such as forms, little eggs and stuff like this for detection of whatever.
Yeah, actually, I feel, I mean, yeah, we went for water quality, but the thing is, I guess it has like many different applications. For example, like in beer industry, you might be able to like analyze the quality of beer, right? So what I mean is that like in cases that you have like more stationary environments, it should, even now, it should be really useful. But like for more dynamic environments, like, I mean, it was visionary, the girl who was like using the watch to estimate the water quality, it was super visionary. And it's really hard to achieve, like at least in near future, I feel, because I mean, there are so many different things in the environment, as you said, like the temperature, the distance, everything is different. But like in more stationary in the industrial use cases, I guess it can be useful even now. Sorry?
Why?
Yeah, why not? Why not go? Actually, we were thinking about it, so.
Make more sense. Like, I'm not sure if that's the way the performance to use Bluetooth or Wi-Fi, things of for Ethernet frequency, because you can basically not use a smartwatch with a specific router like your smartphone. I mean, I don't know, hacking somewhere, I think the smartphone and check the Wi-Fi.
I guess we cannot go for like this granularity with Bluetooth or something, because like we are using 76 gigahertz, which is like super sensitive to small differences in the radar cross section. But as you go for higher and lower frequencies, this sensitivity decreases. For example, if you use like 2 gigahertz or something, it penetrates through the water, and you wouldn't even get a reflection from the water itself. So it's a bit problematic, I would say. I'm not sure if you can use it for this level of innocence.
And what about the 5G? So smartphones has 5G.
Honestly, for water, I don't think even 5G is enough. For example, there was a work on glucose level detection using millimeter wave radar, and they showed that the minimum frequency that you need for it is like around 60 gigahertz for glucose detection. So I feel it's not so feasible to use like really low frequencies. But the radar is super cheap, so it's like 30 euros. So basically, you can, I mean, we have a plan to integrate it in a watch for a different work for body composition analysis in KIT. I guess, I mean, it's affordable for the companies to include it in the watch. Yeah.
About simply using those paper stripes and then you put the water on top and then you turn it. That's much cheaper.
Well, the thing is like the quality is a bit like questionable there. I'm not sure like how accurate you can like how accurately you can use them. And the thing is like the radar is obviously more dynamic. So you can use it like for different use cases, not just for water. You can use it, as I told you, like for wine, for whatever. So yeah.
Because like chemical problem, right? So you chemical problem solution.
Could be. Could be, honestly. Yeah, sure.
Yeah, there's another question. Is the accuracy and is definitely for this or you another way?
Well,
Specificity or
no, actually, I didn't go for another metric, so it was just accuracy because we didn't have space, and it was just 4 pages, honestly. So I didn't go for like more metrics. Yeah, I cannot answer that question right now, but yeah, yeah. Well, I mean, like, I don't have any specific results, but I would say that the results were reliable because I had some other metrics for myself, not for the paper, because there were no like space to include. But no, there was no like let's say what is this overfitting case or anything. So like the results were reliable, I assure you. But well, for the extension, yeah, I'm considering obviously to include like more reliable results. Okay.
It would be super nice to order a few bottles of Amarum just to for scientific.
Yeah, exactly. Sorry.
Is it admissible to buy from bottles?
Yeah, oh, we want to just taste it actually. So that's
So you are invited, Mike.
that's great. Okay,
All right.
thank you. Thank you.
That way you jump out the move. That's available.
Okay. Hello everyone. I'm going to present my previous work is heterogeneous traffic optimization in cellular uplink using machine learning. And first of all, I would like to introduce the optimization scenario. Let's consider a very simple scenario. We have two users, A and B, and the user A will always generate L packet per slot, and the user B will always generate one packet per time slot. And we have a wireless link between the user and the base station. But the link capacity is limited, so only L packet, the capacity is L, so only L packet can be transmitted from the user to the base station. So let's consider two scheduling policy. The base station can select which user can transmit their packet to base station. And we have a two policy. Policy one is round robin. The user A and B transmit their packet to the base station by shifting. So we can easily calculate the average throughput is L plus 1/2, and the average edge of information is 1. On the other hand, policy 2 will make will select user B every L slot, and on the other hand, the rest 10 slot will be allocated to user A, and in that case, the average network throughput will be L. However, the edge of information will larger than 1. So this is a trade-off. In policy 1, in policy 2 has a larger throughput, but also large edge of information. So we would like to optimize this condition. We hope we can reach maximize throughput and the minimal edge of information. So how can we handle more user with different traffic pattern? And I would like to skip this part because I guess everyone knows actually in recent years, edge information can be used to measure the data freshness, and is a good metrics for us to measure network performance. So so we would like to optimize the traffic of the network based on these two, in terms of these two traffic network performance index. So I was trying to model the network traffic. I consider to use periodic periodic packets, which means the packet will repeat in a specific frequency. I can okay. I can use this most so here we have we define these packet frequency to represent the packet, how is the packet be transmitted in a specific time, and the other traffic type is burst packet. We would like to use a stochastic process to model the real network traffic. And in this model, the traffic can be represented by three parameters. The first one, V, is the duration of the traffic flow, and the R is the arrival, the number of traffic flow, and the L is the length per packet. So why we use this PPBP model to model the traffic flow? The reason comes from the research, the previous research. We can see in this figure. In the left-hand side is the real traffic, and the time scale from top to bottom, the scale reduce. So, but we can see the similarity in between different scales. They look very similar. And the right-hand side, was produced by computer simulation. We can see the computer simulation only use the Poisson process to generate the traffic model, the network traffic. However, the similarity is not 100% mapping exactly, but the statistic features can still be kept in this computer simulation. So we choose to use this PPBP model to model the real traffic because we don't have equipment or something to capture this traffic. And based on this PPBP model, there was some assume each user transmit maximum capacity of the on process, and also the user are independent of each other, and the traffic duration is based on the heavy tail duration distribution. So based on this model, we assume the packet arrival will follow the exponential distribution, and the duration of the flow will follow the product distribution, and also the sum of the packet per time slot will have these shift. And in our scenario, we simulate the system, the wireless transmission system, using this notation. We assume in each time slot, we use the Sn of t to represent and user be select to transmission data. If the Sn of t is 1, means the user was selected to transmit. Otherwise, the Sn of t will be 0. In addition, we use another Bn of t to represent how much bandwidth be allocated to the user. And there's the constraint. The sum of all the allocated bandwidth should be equal to the link capacity. And we use the vector S of t to represent this allocation per time slot. And next we have the number of packets generated at time slot t by user n. When denote it at is at Sn of t, and then we can calculate the edge of information is follow this formula. When if the packet be transmitted to the base station, then the edge of information at the base station will be calculated by this t minus t gn of I. Otherwise, the edge of information will increase by 1. And then we use this formula to measure the utility, the source. So
Can you go back one slide, 1 second?
yes.
Sn is the bandwidth that you reserve to the end user, right?
No, Sn is the
Sn, right? Because in the previous slide, if I'm not wrong, right, because I might have missed some part. But in the previous slide, you said that, can you go back one more slide here, right? Possible schedule of D is S1 and S2, where S and, right, Sn is binary, sorry, so, okay, sorry, that's fine. So Bn is the bandwidth that you allocate.
yeah, yes, Bn is the allocation.
Okay, sorry to interrupt you.
So we use these two formula to denote the network utility. We translate the throughput occupied by all the users as this formula. And we use this formula because it's a sigmoid function. We would like to make sure the maximum value happen only exactly the all the link capacity be used by all the users. This what we expect in our optimization calculation. So next, we will have a joint objective function, and this objective function is not linear. It's non-linear. So when trying to use neural network, use the deep reinforcement learning to find the optimal policy for this objective function. And we consider use this model because this algorithm proximal policy optimization algorithm, because the algorithm was proved to efficient reach the convergence, and this can be learned compared to the other different different neural network based algorithm. So we leverage this algorithm to do our simulation, and here we have some simulation model parameters. We revise the N3 simulator to build this base station environment. We choose different we use different random seed, and the unit we distribute all the users in 80 square meter 80 square meter area, and we have different traffic load, user traffic load. So basically, we also have different frequency, arrival frequency for the periodic traffic. And when set up the simulation time is 900 seconds. And this the simulation result. So we can see if the base station can provide enough radio resource per time slot, and which means the high-low traffic of the user is very less than 20%. And in that case, no network backlog. So when compare with our this deep reinforcement learning method with the other round robin and also the proportional fair algorithm, we can find the other two algorithms can also reach the similar performance as the deep reinforcement learning algorithm. However, if the number of high-low UE increase, and the network performance will become worse, because more packet, the traffic flow will accumulate at the UE side. So this will be the opportunity for the PPO algorithm can reach better performance. And so to conclude this research, we formulate the resource management problem, and also provide the design of the traffic modeling. We consider the computer simulation to model the real traffic, even we don't have the resource to capture the real traffic. So in our future work, we will consider more learning-based optimization algorithm. And that will be all my presentation. Thank you. Yeah.
Thank you for your presentation. Can you go back to the simulation results?
Yes.
Yeah. I was wondering, is any of them like proposed for you, or they are like just state of the art algorithms, the models that you have there already? I mean, PPO I know already, and also Rondo. So
Yes.
like, did you include your work here as well, or it's just the works that are already there in the literature?
PPO, I implement the, I implement the PPO algorithm actually, and so the algorithm was proposed by Facebook and OpenAI. So they basically use this algorithm to train the vision based to solve the vision based problem, and I use this to do another task. Yeah.
So then the innovation is in the application part, right?
Yeah, I think, yeah, and also I think when successfully prove like when depends on different traffic load, we can have the throughput, the network utility, and also LI is a kind of trade-off. We can find a balance between these two network performance index. Yes. Yes, thank you.
I have another question. So is this online reinforcement learning approach? So do you learn while you schedule the nodes? Or do you pre-train the model and then you apply the strategy that you have learned offline in the system?
I think it can be online or offline. I can set up the PPO model update frequency. So it can be online, because when when the algorithm continuously receive the packet from users, the model can always be updated.
So the results that you showed us have been obtained by assuming an online learning, because in that case it would depend on the length of the simulation, right?
Yes.
Or will you train a model offline and then you apply the result to the
I in this result I train model offline, but I can so when the distribution change, I think I can still update the model, because it's the model update frequency can be decided by us. So yeah.
This was my second question. So how fast does the model learn a new distribution if the scenario changes, right? Because the mixing of nodes with a certain type of problem might be dynamic, might change over time. So it would be interesting to see how your model is able, your say solution is able to track possible changes in the mixture of the source.
Yes, there's a big challenge to reach, because it also depends on how you choose your redundancy. And if you choose a very unlucky redundancy, it will consume a lot. I can say if I use a desktop with NVIDIA P100 GPU, and you can consume maybe 2 days to reach conversion. Yeah. The worst case. Yeah. So you can continue to run this program in the chain. And the best case is can be converged in maybe 4,000 with 4,000 epoch. It can.
Stops, right?
Yeah. Yes.
So usually when you see those reinforcement learning approaches and so on, is that they might bring you some insight on the real world. I mean, on what is happening. Do you think brought some like new solution or some new insights on how we could adapt some round robin or some proportional fair solution. So do you think that the reinforcement learning solution have brought some insight on how could we derive a fixed solution to your problem or not yet? Meaning, would you derive maybe an algorithm, a fixed algorithm out from your reinforcement solution? Or do you think it's not possible from what you
Yeah, I think I think your question is very great. If we use reinforcement learning to learn the traffic pattern, and then we assume the pattern is not changed anymore, we can use this parameter to fit in the proportion fair, and then we don't need to learn. Yeah. So
something like that.
yeah.
But could so you haven't observed anything like that so far?
You know. Yeah. Based follow your question. I think if the network environment is fixed and we already know the traffic the traffic feature, the traffic pattern in this network, we can easily use the fixed rule-based algorithm to reach the similar performance. Yes.
So maybe another question. So when I look at the plot to the right, So and then you show the average throughput, and the range is between 40 Mbit and 44 Mbit, right? So this is something that the whole difference, right, in if you observe. So from a practical point of view, when I'm in some application, for example, I don't see that it's a big problem. It's 40 or 44. Maybe it's not. I don't know an application where it's so critical. So it's a big problem. So I'm wondering if there are some other metrics that should highlight better this impact that we want to do.
I think yes. I also consider to use the other metrics, and these 40 actually it depends on my I choose the best station parameter. I choose the nomenology is 0, and also and also I only have 20 megahertz bandwidth. So if I use another full capacity of the base station, the maximum of the throughput will be higher than these 44.
So what I think maybe also interesting is not only on the average, but on the kind of worst percentile or so the kind of worst case scenarios where for some applications it can be much more critical. Right? So if you have an increased duration throughput and you want to avoid some realistic and you put worst cases. And then maybe you can see better behavior or insight or improvements depending on application.
Yeah, maybe I need to go, but I mean, it's kind of some fairness also, to introduce some fairness. To form of the user.
Oh, yes, 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 I think that's a very, yes, that's a great direction I can consider to maybe some users was starvation. Some user was starvation in this scheduling